Okay, today we're going to continue our lecture, the last part of Lecture 2, buffer overflow. So let me switch to the slides. You see, there are a number of ways to prevent buffer overflows. The first option is for developer to change their code. For example, they can use safer functions like a string copy or string cat. With those functions, you are going to pass in the buffer length. So this function will know how long the buffer is and avoid copying over the buffer. So the second option is to use a safe language. So common safe programming language like Rust and Go, right? Those kind of programming languages, they will provide a lot of support to prevent memory vulnerabilities. For example, most of those languages, they have something called a garbage connection. So you don't have to allocate or free your memory by yourself. Right? It will also add in a runtime check to make sure the buffer will not be overflow. Okay, so try to use a safe language if you are going to start a new project. So the second approach is OS-based, called address space layout randomization. In this defense, so the OS kernel will move the program's code sections, the stack, and the heap to a random location. So by doing so, the attacker cannot know prehand, right, where those targets are located. Like such, as we have mentioned, right, to exploit the buffer overflows, you often need to know the address of the offset of the return address, right? And also the runtime address of your shellcode. So by randomize the layout of the stack or heap, so it will make it very hard for attacker to know the runtime address of those components. So ASLR has been enabled in all the major operating systems, including Linux, Windows, and Mac OS, and also all kinds of BSDs. So the third approach is compiler-based. So every time when you build your new program, you can tell the compiler to insert something called an inline reference monitor. Which are small pieces of code inserted into your program to enforce some kind of security policy. Okay, so the stack guard is a compiler-based approach. We're going to look into the details. So the fourth approach is hardware-based. Sometimes, so it's called a non-executable stack, or the DEP, data execution prevention. So address-based layout randomization. So as we have mentioned, right? So the attacker needs to know the address of various targets. In the buffer overflow, you need to know the offset of the return address. So this is task A. In the task B, you need to know the real-time address of the shellcode. So if we can randomize the memory layout, it will make it harder for attacker to guess those addresses. So most current systems support randomize the stack, the heap, and the data section. So to randomize the code section, your program must be compiled as a position-independent executable. So the position-independent executable means that your code can be executed anywhere in your address space. It's a special type of construction for your program, which will enable your code to be executed anywhere in the address space. So every time the code is loaded in the memory, the stack address will change. This will make it difficult to guess the stack address in the memory, and also difficult to guess the EBP address and the address of malicious code. So this will make the attacks task much more difficult. So here we have an example. This is a very simple program. We have some local variables, so x and y. We also allocated this will be 12 bytes from the heap. So this is on the heap. So those two are on the stack. Then we're going to print out the address of buffer x, then the address of the buffer y. So here is the example. We have mentioned it before, so the randomization in the Linux kernel is controlled by this parameter, randomize VA space. If it's set to 0, it means not randomized. So if you run your program on this condition, every time it will return the same address. So here we see the x, right? Here, the second run, it will give the same result. If this number is set to 1, it means randomize the stack only. So we get a different address for the stack, but the same address for the heap. Okay, so if the variable is set to 2, it means randomize the stack and the heap, both stack and the heap. So we get a different address for the stack and also the different address for the heap. So if you look at those numbers, okay, so because this is on the 32-bit architecture, so the difference between this randomized number is actually not huge, right? If we look at this, we have BF, then they both have BF. The third number will be F, this will be E. So F in the binary will be 1111, right? 4 ones. E will be 1110. So those two addresses, let's say 9C 76F0 E69700. Okay, they have this is 4 bits, another 4 bits, 8, 11 bits. So the first 11 bits are the same, right? And also because of the way the stack is organized, so the last 4 bits are also the same. So the difference, or the entropy, will be 32 bits minus 11 minus 4. That will equal to 17 bits. Okay, so it means that if you try to break it using brute force means that you're just going to try again and again until you get lucky, right? So you need to try 2 to the power of 17 times and divided by 2. So you need to try 2 to the power of 16 times on average to break ASLR on the 32-bit architecture. But for 64-bit architecture, it will be much harder, right? Because you have much larger address space to play with. Okay, so by passing the ASLR, so the first one is to use brute force attack, as we have mentioned in the previous page, right? It take on average 2 to the power of 16 to break the ASLR on the stack. So we can also use a ROP. This is called a return-oriented programming. To exploit the non-randomized memory. So basically, ROP means it's a type of code reuse attack. So we're going to talk about this in the next lecture when we are talking about a return to libc attack. So instead of like injecting the shellcode as we have done in the project 2, you are going to use the program's existing code to launch the attack. If you think about it, right? So a normal program usually has a lot of code being loaded into the address space. Like libc is actually huge, right? It contains a lot of interesting functions, like system. So the system function take a parameter of the string, which is the command line. For example, you can say user or the bin as such. So this will, if you call this system function with this parameter, it's going to create a new shell. Okay, so there are actually some non-randomized memory in most of the program. For example, if the code or the program or the library are not compiled as PIE, so we have mentioned it, right? If you need to randomize code, a program must be compiled as a position-independent executable. Okay, so if you have a library which are not compiled as a PIE, then it must be loaded at a fixed location. Right, so this will defeat the address space nail randomization. So system can also have ASLR off by default for compatibility. But this was the situation in a few years ago. So when the Windows first introduced the ASLR, they turned it off by default to be compatible with all kinds of applications. The biggest problem to them is actually the Microsoft Office. So the Office is a huge program. It has a lot of compatibility issues with ASLR, but now everything is fine. You can also exploit the information disclosure bug to review the addresses. So the information disclosure, basically you are going to leak the information. So sometimes this is called information leaks. Okay. So the ASLR if you have an information leak vulnerability, they can be exploited to leak the runtime information of your program artifacts. So here is an example, right? To do the ASL, to attack ASLR by brute force. Basically, it means you're going to try it again and again. So we can turn on the ASLR. So we set the VA space to 2. This means the stack and the heap will be randomized. Then we compile the program as before, right? So in your project, you actually set this parameter to 0. This will disable the ASLR. Okay, so here is a script to run the brute force attack in a infinite loop, right? So here is this part means tells the bash. This is a bash script. Okay, the second is a bash built-in variable. It will count how many seconds has passed since the last time this variable is cleared. Okay, so you get the duration from the seconds. Then we calculate the minutes and the seconds. Then we print out the how many minutes and seconds has have passed, and we just keep running the program. Okay, so eventually we're going to get lucky to compromise this stack, even though the stack and the heap have been randomized. So we get the shell after running about 90 minutes on this test machine on a 32-bit Linux. Okay, so here is some output. We get the shell. As we have mentioned before, right? It takes about on average to the power of 16 times to try to brute force this program. Okay, in the Unix or Linux environment, so you can get the memory map of all the processes on something called a proc. So the proc/proc is a pseudo directory or pseudo file system on the Linux or Unix system. So it contains a lot of information. It's not a real directory on your disk, but a virtual directory created by operating system. For example, it contains CPU info, like what kind of a CPU you have and how many CPU cores. In this case, we have only a single CPU core because when we created the virtual machine, we only assign it a single CPU core. So there is also the memory info, like how much memory you have. So on this virtual machine, we have 8 GB of virtual memory. So under the sys kernel, there are a lot of runtime parameters for the kernel. So this is the current directory /proc /sys /kernel. So for example, the randomized VS space, it's actually a parameter in the kernel. We can set this at the runtime using syscontrol. So its current value is set to 2. It means that we can randomize both the kernel and both the stack and the heap. So on the proc, there is a directory for every running process. Like say 2048, this will be our process ID of 2048. So if we go to 2048, so there are a number of files here. We can cat cmd9. Okay, so this is actually the SSHD, the OpenSSL server. So we can also cat the maps. Okay, oops, it says let's pick another process. Let's cd 2098 cat cmd9. This will be the bash. It will actually be this bash process. So we can also cat the maps. It shows the memory map of this this process. So for each line will be a new section. So look at the first line. It has permission over readable, executable, and the present. So this will be the code section. The second line is readable and the present. This will be the read-only data section of the bash process. The third line will be readable, writable, and present. This will be the read-writable data. Okay, so we also have a heap here. So there are a lot of shared libraries, like this one. These 4 lines will be the sections for libc. There is also the stack. Okay, so the proc has a virtual name, like a virtual directory for the current process. For example, we can do cat, let's say, let's search self. Okay, so in here, self is a virtual process ID. It basically points to the current process. So when we cat proc self maps, it will actually cat the memory map of the cat program. Then we will pipe the output to the grep. So it will only show the lines contains heap, stack, libc, and the cat. So let's clear the screen first. Here we run it twice. If you compare this output, right? So the first 3 lines, they are actually the same. So it means that this program being cat is not compiled as position independent executable. So this is why the code section and the data sections are not randomized in this process. So the heap, they are different, right? So the first execution and the second execution, they are different. So libc, they are all different for those 2 executions. This is because libc is a shared library. Shared library is always compiled as a position independent. It's not an executable, a position independent executable. Okay, so it can be randomized from each time you executed the process. Then there is also the stack section. So the stack sections are also different. Okay, so next we're going to talk about the stack guard. So the stack guard is a compiler based approach, right? So in this approach, so it's going to embed a random number. So this will be a random number called a canary below the return address. So the assumption is that if you have a buffer below the return address, right, when you try to overflow the return address, you are going to overflow the canary first. So in the function prolog, function prolog is the part when you enter the function, right? So we're going to embed a canary word between the return address and local variables. In the function epilogue means before you return from the function. So we're going to insert the code to check the canary before it returns. If we have a wrong canary, there will be an overflow. There is an overflow being detected. Okay, so this is something called a stack guard. So it's a type of inline reference monitoring. So we have mentioned that inline reference monitoring enforce a policy. So the policy here is that to overflow the return address, it must overflow the canary. Right? To overflow the return address, it must overflow the canary first. Okay, so sometimes this is true, sometimes this is not true. So we're not going to get into too much details about this. So here is a program compiled with stack guard. So here is a part in the function epilogue. It's set the stack canary. So this is the part of the function epilogue. So it will check the canary. So when you read this piece of assembly, so there is one tricky part. It's called a %gs20. This is something called a thread local storage. So the thread local storage, basically it means that for each thread, you are going to have a different memory referenced by %gs20. Okay, so if you have a multiple thread, right? If you have multiple thread running in your program, so each different thread will have different canary. Okay, so I'm not going to get into too much details. Okay, so when we look at this piece of reference monitor, right? We move the canary to EAX, then we move the EAX to EBP minus 12. Then we XOR EAX with EX. So basically, when you XOR a number with itself, you set EAX to 0. Okay, so we use XOR because it's faster than the move instruction. Then in the epilogue, we move the EBP minus 12 into EAX and compare the canary with the EAX. If they are equal, we're going to return from this function. Otherwise, it's going to call the stack check fail function. So this will raise an alert, say the canary has been changed. Okay, so if you pay attention to the canary it actually means that the canary is only set once, or let's not use set, say it's only initialized once when the program starts, right? So %GS, %GS20 is actually points to a memory location. So when you start the program, so the loader will get the random number from the kernel and initialize the canary for each thread at a specific memory location. Okay, so the canary is only initialized once. It means that if your program is running for a very long time, okay, so it's going to have the same canary for a long time. So this can have some security implications. Again, because this is a random number, canary is a random number, make sure you have a high quality random number, right? Never use a constant for random number. So still remember the Sony epic fail, right? In this problem, in this vulnerability, Sony used a constant number for random number. So it will leads to the whole computer system being compromised, whole console system being compromised. Okay, so another defense is called data execution prevention. Right, data execution prevention. So it basically has two parts. So the data cannot be executed, and the code cannot be overwritten. So it means data non-executable data and read-only code. So when we have those two conditions, it means that no new code or the shell code can be introduced to your program, right? So you cannot say, let's inject a shell code onto the stack, then let's execute it, right? So of course you can put the encoding of the shell code to the stack, but it cannot be executed because the protection. So the data cannot be executed, right? So the data, including the stack, the heap, and the data sections. Okay, so as we have mentioned, there are a lot of data sections in your program. It can be the data sections of your main program, right? It can be the data sections of the shared libraries. So some complicated programs like LibreOffice can use hundreds of shared libraries. So there will be a lot of data sections. Okay? And also, you cannot override in the existing code. So you cannot say, okay, so since we cannot executable the data, let's try to overwrite the instructions. Because the code section, right? So the code section has read-only and executable permission. So it's not writable. Okay, so if you have a data section, it's either read-only or read and writable, but never executable. So because of this, right? If we look at this truth table, so the data execution prevention sometimes is called a W XOR X. It means that a piece of memory cannot be writable and executable at the same time. So data execution prevention is often provided or enabled in the hardware, specifically the page tables. So the page table has a lot of permissions, like read, write, execute, the privileges, whether it's a user code or the supervisor code or the kernel code. Okay, so there are a lot of permission bits in the page table. So for example, to set a code section, so you can set a read bits to 1, write bits to 0, and execute bits to 1. Okay, so those are the bits in the page table. Okay, so the data execution prevention prevents you from the injecting new code. Right, so there's no new code in your program. So data execution prevention can be defeated by code reuse attack. Right, so since you cannot introduce new attack code into the program, we can reuse existing code for malicious purpose. Okay, so this is actually a large set of attack method. We're going to talk about this in the next lecture. Okay. So there is also some countermeasures in the bash or the dash. So they will turn set UID process into a non-set UID process. So what is a set UID process? Okay, so set UID process is often needed for programs like password. Okay, so if you think about this, right? So the password allow every user to change their password. Okay, so it means that it can update the password database. So the password database is owned by the root user. So the most privileged user in a Linux system. It cannot be owned by other users, right? So it should only be writable and readable by the root. But every user, so by default, right? So the password program should have the owner of root. So it's owned by root. Okay, but it's being executed by every user in the system. Okay, so normally when you execute a program with a user, it will have the permission of the executable of the executor. Okay, so say if we execute a program with seed, right? So the seed will become the effective user ID of this process. Okay, but a set UID program will allow the program to be executed as if it's by the owner. Okay, so this is implemented in this way. So for each process, so the process is the running instance of your program, right? So for each process, there is a effective UID, and there is a real UID. Okay, for the password program, right? So the effective UID will be root, and the real UID will be seed. So it means that this process is started by the seed user, but when you check the permission for access control purposes, it's actually be checked as the owner of password or the root user. Okay, so you can enable set UID for a program using something called CH mode. Change the permission of your executable, right? Okay, so there is a difference in the bash and the dash. So they're going to turn the set UID process into a non-set UID process. So in our example, right, in our project, so we running we have a vulnerable program called a stack. Okay, so the stack is a set UID program. Okay, so it means that it has it's owned by the root, So when you execute this, okay, with a malicious input, it's going to create a new shell. So in this shell, it's check its effective UID, right? So now it found that the effective UID are different from the real UID. Then it's going to say, make a system call, set the effective UID to the real UID. So this will lower the shell's privilege to the seed in our program, right? So in project 2, we are going to try to defeat these countermeasures. Okay, for example, before running start the shell, you can set the real UID to 0. Okay, by invoking the set UID system call. Okay, so now when the shell try to check for effective UID, now they are the same, so it's not going to reset the shell to the non-set UID process. Let's take a quick look at the password file. So the which command will tell you which binary is being executed when you type this command. So let's do ls-l user bin password. So this is the binary. So it's owned by the root user and also in the root group. So the user or the owner of this program can read it, write to it, and also execute it. So the S bit, it replaces the X bit. Here, the S bit means this is a set UID program. Okay, so the second 3 bits tells the permission of the group. So anyone in this group can read this binary, can also execute this binary. The third 3 bits tells the permission of other users. So the other users can also read and execute this program. So when the other user executes the password program, it will be executed as if it's being executed by the root user. So this is why we can change the password file, right? Okay. Okay, so we have learned a lot about the buffer overflows and how to exploit those simple vulnerabilities in a very limited environment. So the question is, am I a hacker now, right? But the answer is that there is still a very long way to go before you can actually hack a real program. As we have mentioned, right? So the modern operating system has a lot of defenses built into the program. So now some programs, they even have control flow integrated. So this will make exploiting those programs to be much harder, and often they are using sandboxes. So the sandbox is a kind of environment to run the untrusted or malicious code. So the purpose of sandbox is to confine the side effect. So if you compromise some program in the sandbox, right? So it affects the compromise process, but it should not affect anything outside of the sandbox. Okay. So for example, like Chrome browser uses sandbox to render the web pages. So in the real world, to compromise a target like a browser, you need to break all those defenses, including the sandbox, ASLR, DEP, the canary, sometimes also CFI. So in many cases, you need to use a number of exploits and chain those exploits together. Right? So here we have some examples, right? In the Part4 2020, so a team from Georgia Tech used 6 bug chain. So it means that they use 6 exploits one by one in order to compromise the program and to escalate to the root privilege, right? So it will be a long process to actually attack a real program, but it's also could be beneficial, right? So if you still remember what we talked about in the first lecture, so high quality bug or vulnerability or exploits will actually bring some financial support. Okay, so this is the last part of Lecture 2.